Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering.
Good evening everyone, welcome to ACE Online by ACE Engineering Academy. So myself Khadar Basha. Now today we are going to see an important topic in transformers, that is voltage regulation. So this topic is not only related to transformer, also we have in alternators and also in DC generators. Everywhere, generators and transformers, it will be there, voltage regulation. However, in motors we will see speed regulation. In generators and transformers we will see voltage regulation. Now what is the importance of this voltage regulation? So why we need to calculate? So this is one of the performance parameters of generators and transformer. Performance parameter. Now in terms of efficiency, we need a high efficiency transformer, and in terms of regulation, we need a low regulation transformer, a low voltage regulation. That is the best one. But in efficiency, high efficiency is the best. But in regulation, low regulation device is the best one. So voltage regulation, simply voltage drop in the device. That may be generators, that may be transformer, anything. It is what? Just voltage drop in the device. How much voltage will drop for a particular load? Is it less voltage drop or more voltage drop? So which is important? Less voltage is required. Can you avoid total voltage drop first? No. Definitely voltage drop will be there. But how much it is? So as much as possible, voltage drop should be less, minimum. So we don't want maximum regulation. Okay. Now first of all, what is voltage regulation? It is the ratio of change in voltage across the load. It is the ratio of change in voltage across the load from no load condition to full load condition to the no load voltage at a specific power factor of load. Okay. So it is the ratio of change in voltage across the load from no load to full load. Generally we consider as a reference full load. But do we connect always full load? No. Sometimes we connect half load or 60% load or 70% load or 80%, anything. So at any load it is defined. But generally we consider full load condition always, because that is our rated condition. So no load operation to full load operation, how much voltage will drop? So we will consider that voltage drop. Okay, up to full load condition. And it is expressed as a no load voltage. It is expressed as no load voltage at a specific power factor of load. Because we have different power factors like lagging, leading, unity power factor. Same as it is in alternator also. Same as it is in alternator also. So whenever power factor changes, your regulation will change. Generally, let the transformer secondary voltage is 200 volts. Secondary induced EMF is 200. And how much voltage will appear at the load? Whenever we connect load, how much voltage will appear? More than 200 appears, or less than 200, or equal to 200? How much voltage will appear at the load, across the loads? Definitely, it may be less, it may be more, or it may be equal. That depends on what? This load power factor we connect. So it is every time not same. But practically if you talk, what is most of the loads we are connecting practically? Lagging loads of power factor in the range 0.7, 0.8, 0.9. Mostly we operate transformers. So definitely for lagging power factor we get the secondary terminal voltage is less than the induced EMF of secondary. So we get, if EMF is 200 volts, definitely little less than we get. Sometime 197, 196, 195 or 192, in that range. Some 5 to 10 volts will be dropped approximately. So generally practical transformer regulation also, if you see, maximum regulations will be around 4 to 5%. Or take 5% also. 5% of 200 means some 10 volts will drop, maximum. Generally 4 volts, 5 volts, 6 volts, that fluctuations will be there. So in our homes also, whenever we check the stabilizers particularly, so whenever digital readings are there in that, we can observe that voltage will not be steady always. Sometime 230, sometime 227, 228 or 222, 225. That voltages will fluctuate. That depends on the load operation. Whenever loads are changing, drops also will change. That's why that variations of voltages will be there. Approximately 4 to 5% will change that voltages. whatever we are getting, that single phase. Now, what is the importance of knowing voltage regulation of transformer is in order to maintain a proper voltage to loads, because if you don't maintain proper voltage to load, load will suffer with that. Sudden increase in voltages or decrease in voltages. At low voltages, generally the loads, particularly motors, will draw some high currents at low voltages. So when we get low voltage, if most of the voltage will drop in transformer itself, so low voltages we get. Under low voltage condition, transformers, loads, particularly loads under low voltages, will draw high currents. Then overheating of these motors takes place. Overheating means they may damage. That's why we need to maintain a proper voltage to loads, almost constant voltage. For that, what we do in most of the transformers in substations, we have tap changers. Tap changers will be there. So based on the percentage regulation at a particular load, we have some percentage of tap changing. 4% tapping, 5% tapping, 2% tapping, tap up, tap down we call. Tap up we do generally for lagging power factor and tap down for leading power factors, because whenever loads are leading, capacitive loads, receiving end voltages will increase. Just like in power system, you know, transmission lines also. When capacitive loads are connected to transformer, the terminal voltage across the loads will be more than EMF of transformer. Suppose 200 is transformer secondary EMF. At the terminal for capacitive load, terminal voltage will be more than the 200. Let us take some 205 volts. Then what happened? Direction of current will reverse, no? Receiving end voltage is more than sending end voltage. Then if receiving end voltage is also high, loads may damage. So there we do tap down now. Tap down we do. And whenever there is lagging power factor loads, regulation will be positive. Voltage drop will be there. So we do tap up there. Tap up means some turns we increase. Some turns we increase. Whenever turns increase, automatically voltage rating will increase. Then load voltage will be maintained properly. So it is very important to know practically the voltage regulation of transformers, so that a proper voltage we can maintain at the loads by doing tap changing, by using tap changers. Okay. Now let us consider a equivalent circuit of transformer first, refer to secondary side. Okay. From that circuit we will analyze. So when we get positive regulation, when we will get negative regulation, when we will get zero regulation. So all we will observe with the phasor diagram now. Okay. How we are getting positive, at what load we get positive, at what load we get negative, at what load we get zero regulation. So many times in JE examination of SSC JE or RRB JE or most of the competitive exams, direct questions on this regulation topic. So if you know little concept about this, you can answer so many questions in so many examinations directly just by reading the question. But you should have clarity in this first, how regulation is changing. So when we get zero regulation, what happens if zero regulation? Or what is the problem with maximum regulation? Okay, so let's see one by one. Now let us consider equivalent circuit of transformer. Equivalent circuit of transformer. Refer to secondary side. Refer to secondary. So here we neglect the no load branch or no load current. Now this is the equivalent circuit of transformer. Refer to secondary side. Total resistance on secondary R02 and total reactance on secondary X02. So this is our load condition. Let this is the EMF induced secondary side E2. Load is right now switch open condition, means no load condition it is. Let us place one voltmeter also here if you want to check the voltage we are getting across the load condition, across the load, under no load and also full load. So right now as it is no load, this is R02 first, X02. Right now it is no load, no current here. Let EMF E2 is some 200 volts, no load voltage. This is called no load voltage, or voltage induced on secondary under no load condition, or secondary induced EMF simply. This is the no load voltage. Because whenever switch open, no current, the voltmeter reading will be the no load voltage. No load voltage is no load voltage equal to that E2 whatever we are getting. So example, let us take 200 volts. 200 volts. That is the no load voltage. Same EMF will appear across the load whenever it is not connected, switch is not closed, means no load condition it is. No voltage drop, total voltage appears, or total voltage will be read by this voltmeter here. Okay, this is no load voltage. Now let us close the switch and assume that the load is full load here. Full load means what? Whatever this transformer capacity, suppose 10 kVA capacity of transformer, same 10 kVA load is connected. Now, assuming it is full load, under full load, what is the voltmeter reading? Let it is V2. How much it is? Let us take lagging power factor for example. Definitely voltage drop will be there. Whenever load is connected, a full load current will flow here, some drop across resistor and drop across reactor. So voltage will drop out of 200, let some 10 volts is drop in both resistor and reactor. Then the voltage across load we are getting 190 volt. This is called full load voltage. Whenever switch open, the voltmeter is showing 200 volts. Whenever same switch is closed, the same voltmeter showing 190 volts. So how much change observed? No load to full load condition. No load to full load, how much change is observed? 10 volts change is observed. Now this voltage change we will express as a no load voltage. Therefore, what is the regulation? According to definition, it is the ratio of change in voltage from no load to full load to the no load voltage. This is in per unit. If you want percentage regulation, multiply the same value with 100. E2 minus V2 by E2 into 100. This is percentage regulation. Okay. Now we have to check this difference. Whenever E2 is greater than V2, we get positive regulation. So right now E2 is 200, V2 is 190, so greater. That's why positive regulation we get. And sometimes we may get zero regulation also. So when we get zero, whenever this E2 equals to V2, if both voltages are equal, then zero regulation it is. If this EMF E2 is less than V2, suppose the terminal voltage we are getting high voltage than this E2, then negative regulation we get. That depends on the loads we connect. So we may get here positive regulation, or we may get zero regulation, or we may get negative regulation. This type of regulation depends on loads, load power factor. We have three types of loads: lagging, leading and UPF. So I will show you with a phasor diagram all the three cases, how the regulation will change, positive value, negative value and zero value. Okay. For that, we need to consider an equivalent, from this equivalent circuit, we need to consider KVL equation. This is the EMF induced, E2, and this is the terminal voltage we are getting, V2, across the load. Whenever full load is connected, let full load is this. Otherwise, any load also we can define regulation, not only full load. Because always can we operate transformers at full load only, always, 24 hours? No. If you take distribution transformer particularly, the load on the transformer may not be same in throughout 24 hours. Sometimes 50% load, sometimes 40%, sometimes 60%. So these loads will fluctuate. But generally we take maximum drop is possible only at full load condition. Full load means high currents or rated current. So maximum voltage drop will be taking place. That's why we consider full load operation always. Okay. Now from this applying KVL, the EMF induced E2 we can write as E2 is equal to vector sum of, so this EMF equal to terminal voltage V2 plus drops in this. Terminal voltage V2 plus drops. I2 R02 drop and I2 X02 drop, reactance drop. Okay, so this is the equation. Now this equation we will utilize to draw the phasor diagram for different types of loads, like lagging power factor, leading power factor and unity power factor. Now let us see one by one. First, case 1. So only phasor diagrams I will draw to show you whether it is positive regulation or zero regulation or negative regulation. Okay, see here. Case 1. Case 1. lagging power factor load. Lagging power factor load means RL load it is. So this is the practical case also. See what happened here. Which is greater? Regulation is positive or negative? Let us check. So always we take from this equation V2 is the reference. V2 is the reference. This is V2. Considering terminal voltage reference. Now, as load is lagging power factor, some cos phi lagging, 0.8 lag for example, some cos phi anything, cos phi lag, anything it is. Now what is the angle here? Cos phi equal to some 0.8, then phi equal to 36.86. Now current lags this voltage by some angle, that is power factor angle phi. Okay. Whenever there is load, as current is passing, drops will come into picture. Now resistance drop, reactance drop takes place. So resistance drop will be in phase with the current. This is I2R02 drop. And reactance drop perpendicular to this. This is reactance drop perpendicular to resistance drop always. Now what is the vector sum of these three vectors? The vector sum of these three is nothing but E2 only, no? Now let us join these three resultant. This is E2 it is. This is the resultant of the three vectors V2, I2R02, I2X02. So this is E2. Now just observe from the diagram which magnitude is greater from this. Whether E2 is greater or V2 is greater. Definitely if you see the phasor magnitudes, this is the magnitude of V2 and this is the magnitude of E2. Which magnitude is greater? E2 is greater, no? E2 greater than V2 from this. So as E2 greater than V2, what is the difference we get? Positive value. Therefore, regulation is nothing but proportional to E2 minus V2 difference divided by E2, that is always positive value. But this difference we have to check. Which is greater here? E2 greater. So we get positive regulation it is. So here we got positive regulation. And how much regulation it is? How much regulation it is? Tell me. How much regulation? So this is where we have some value, some equation is there. We have some equation, how much it is. So that equation of regulation is, just remember this, I am writing directly. The percentage regulation magnitude is percentage or cos phi, percentage or cos phi plus percentage x sin phi. So this is the equation for lagging power factor. If it is leading, the only difference there is here minus will come. This is the plus for lagging power factor. If it is leading power factor, then we take minus here. So plus for lagging, minus for leading. Just remember this, plus for lag, minus for lead. This is the equation of regulation. So this much magnitude is the regulation. If you want how much regulation, 3% or 4% or 5%, use this equation from the data given in the question. And substitute here, you will get the value, how much regulation it is. Positive regulation definitely for lagging power factor. Okay. Now let's see for unity power factor, what is the regulation. Let's see for unity power factor, what is the regulation, whether it is positive, 0 or negative. Same as it is. Let's see that. Case 2. Case 2. UPF load, unity power factor load. Or purely resistive load it is. Purely resistive load. Observe here. Same equation, whatever we have taken previous KVL, this one, same equation we take again, E2 equals to V2 plus I2R02 plus JI2X02. Same equation we will utilize now to draw the phasor diagram for UPF. Again V2 only reference, terminal voltage is always reference for us. This is V2. As load is unity power factor, cos phi equal to 1, angle is 0, means current is in phase with the voltage. This is the current I2. This is the current. when there is a current, drops will come into picture again. So resistance drop, reactance drop, continue from the voltages. This is I2R02, resistance drop. And this is reactance drop I2X02. Now the resultant of these three is EMF E2 again. This is E2. Now from the diagram, you can observe or you can check which magnitude is still greater. This is the magnitude of V2. This is magnitude of E2. Which is greater still? Still E2 only greater. Still the magnitude of E2 greater than V2. So what is the difference of these two we get? Regulation proportional to E2 minus V2. Still E2 greater than V2, no? So we get positive regulation only. But how much positive it is? Compared to previous, how much positive? More or less? So previously lagging power factor, check the diagram once, this one. So whenever the current I2 is here, this much is the E2 we got. So still E2 greater than V2 here, positive regulation it is. Now I2 is moving towards UPF like this. Whenever I2 moves in this direction, I2R02 also will move like this. If these two are fixed one, these two are just like this perpendicular. So whenever it is moving like this, it will also move like this. These two are exactly perpendicular, no? You can also fix these two vectors. Fixed it is. They are perpendicular always. Whenever I2R02 moving in this direction, I2X02 will move in this direction. Then as I2X02 moving towards this, what is the magnitude of E2 here? Slowly decrease. Okay, so we got UPF, this one. Even it is decreasing, but still E2 greater than V2 only, no? Yes, that's why regulation still positive here. Regulation is still positive, but how much it is? Less than lagging power factor. Suppose in lagging power factor you got 4%. Now you will get less than that, some 2% or 1.5% like that. And if you want to find percentage regulation, how much? The equation is, the percentage regulation for UPF is only percentage R. Just take this equation. This is the percentage regulation for unity power factor. Why it is? You check the same previous equation. UPF means cos phi equal to 1. Whenever cos phi is 1, what is sin phi? 0 it is, because phi equal to 0. Cos phi equal to 1 means phi is 0 degrees. Sin 0 is 0. So this term totally 0, only percentage R is left. So this is the equation for UPF case. And for leading power factor, same equation, we have to take minus. Okay. Now let's see. Compared to lagging, for UPF regulation is positive but less than lagging power factor. Let's see what happened now for leading. Here little bit you can guess. See what happened. Let us move current. Leading means what? Current leads the voltage now. Current leads the voltage towards this. Whenever I2 is moving in this direction, this I2R02 also will move like this, and I2X02 will come like this. So slowly this E2 will reduce still further. Up to that positive regulation only we get. Up to some region positive regulation. After that, at one of the power factor, E2 equals to V2 we get. Then regulation 0. And still if you move this current I2 towards leading, more leading, we get negative regulation also here. In the leading power factor, we will get three types of regulations: positive, 0 and a negative. Okay, let's see briefly the three figures. I will show you three variations in the case 3. Case 3, leading power factor load. Leading power factor. Now, there are three subcases here. The first one is this. So I will take, this is V2. V2. Now I will take the current I2 compared to the previous UPF, just leading, little bit leads I will take. Just current leads now, little bit, some 5 degrees, 6 degrees. Current leads. Then I2R02 also just leads from previous, I2R02. Resistance drop in phase with current, and reactance drop is this, I2X02. And if you take the resultant, this is E2. Okay. Now in this diagram also you can check which magnitude still greater here. This is V2, this is E2. Which is greater? Still E2 greater, no? Yes. Still E2 greater than V2 only. Therefore, the regulation we get here positive value. difference we get positive only. But what is this value compared to UPF? Less, because in UPF we got some more difference, but that difference now reduced for leading power factor. So positive but less than UPF. See, if you have a clarity on these diagrams, you can understand the regulation curve easily. So finally we draw all the three cases combining with a graph. That is called regulation curve. So if you know the clarity of that regulation curve, so many questions directly you can answer. Okay, this is first case in leading power factor. Now let's see the second sub case. So slowly I will take the current towards more leading, little bit leads, and then more leads, and then more leads. If current is moving in this direction, this E2 will reduce. At one of the power factor, both will be equal. Then we get zero regulation. And after that, negative. Let's see this. Clear up to this? How we are getting regulation variation, positive, negative, zero. Now let's see zero regulation it is. Second sub case. Same V2 is the reference. Current I2, little more leading I am taking. This is I2. Then I2 R02 drop parallel to current. And let this is I2 X02 drop perpendicular to resistance. Let this is the resultant of the three vectors. E2 it is. Let us assume approximately here the magnitude of E2 equals to V2 approximately. So as both are equal, as magnitude of E2 equals to V2, as both are equal, what is the regulation we get? Zero here, because difference now it is. Regulation proportional to E2 minus V2. As both equal, right now, regulation zero. So zero regulation we get at one of the leading power factor. Okay. Now let us move the current still more leading towards this. Then we get negative regulation. Okay. So let's see the third sub case. Third one. Third. Considering same V2 as reference, current I2 still more leading than previous. This is I2. And I2 R02 parallel to the current or in phase with current. And I2 X02 perpendicular to this. Then the resultant of these three is nothing but E2. Now what is magnitude of E2 here compared to previous? Reduces than V2. So as E2 now less than V2, what happened? The regulation we get negative value, no? So regulation will be negative here. So therefore the regulation proportional to E2 minus V2. So we will get negative value. Negative regulation it is. So only for leading power factor, we get three types of regulation: positive, zero, and negative. And most of the region which regulation we get for leading is negative only we get. Most of the region. For most of the power factors in leading, negative. Very small region we get positive regulation. At one of the value we get zero regulation. Okay. Now the percentage regulation for leading is, magnitude is this much. Percentage or cos phi minus percentage x sin phi. So minus we take in the same equation. This is the equation for leading power factor. Okay. Now we will combine all these three cases into a graph called regulation curve. Clear up to here? Any doubt up to this? Any doubt up to this? Now all these three cases we combine as a regulation curve. Let's see that. Regulation curve. Regulation curve. So if you remember this graph enough for most of the questions, regulation curve. So it is drawn between the magnitude of regulation and power factor variation. So on y-axis we take regulation, positive regulation, and here negative regulation. This is power factor variation. Power factor. The reference power factor is unity power factor. At the origin we take UPF. And towards right side, let us take lagging power factor. Maximum power factor is 1, minimum power factor is 0. So towards left side, I am taking leading power factor. So lagging side, 0.8 lag, 0.6 lag, 0.4 lag, 0.2 lag, 0 power factor. Similarly, in the leading, 0.8 leading, 0.6 leading, 0.4 leading, 0.2 leading, and 0 power factor leading. Now, what is the regulation we got for UPF? Positive, no? Check the previous. The regulation at UPF is positive. Let this much is positive. Now, if you go from unity power factor to lagging side, what is the value of regulation? Difference between E2 and V2 increase. Check the diagram once. The regulation increases towards lagging, and somewhere here we get maximum regulation near to this 0 power factor. Somewhere 0.1, 0.2 something. Okay. And if you move from unity power factor to leading side, what happens? Slowly that regulation decreases to 0. Slowly this regulation decreases to 0. And after that becomes negativities. So this is our 0 regulation. Here we are getting 0. Remember, this 0 regulation mostly possible between 0.9 and unity power factor. Somewhere, some 0.92, 93, 94 or 96. Somewhere we get 0 regulation. Between 0.9 and 1, most of the cases. Okay. And positive regulation at unity power factor. And this is our maximum regulation. Maximum regulation. So all the previous 3 cases we combined as a single graph. That is called regulation curve it is. Okay. Now you may get questions here directly. If regulation at 0.8 lagging is some 10%, what is the regulation at 0.8 leading? Is it minus 10%? No. Because at 0.8 lagging, observe this one. At 0.8 lagging, whatever the magnitude of regulation we have, at 0.8 leading, we don't have the same magnitude of regulation, different it is. This is not same, because this regulation curve is first unsymmetrical curve. That is important. This is unsymmetrical. Positive peak is more, negative peak is small. Positive peak is more, negative peak is small. So it is unsymmetrical. If this value is 10%, this is not 10%. So this is negative value, but less than 10, like minus 4% or minus 5% like this. Negative, but less than 10. So such type of questions you need to take care for examination point of view. Now, generally we have some other questions like what is the condition for maximum regulation, or what is the condition for 0 regulation? At which power factor we get maximum regulation? At which power factor we get 0 regulation? And first of all, tell me, is it required maximum regulation? No. So we don't want maximum. And do we require 0 regulation? No. 0 also not required. These two are the critical points for us. So in between the 2 points only we prefer to operate, but not maximum regulation, but not 0 regulation. Because practically our operation of transformer is in this range only. Some 0.7 to 1 UPF. In that range only we operate. So we don't want maximum. So then why we are calculating that condition for maximum? Suppose you know that maximum regulation we get at 0.2 lagging power factor, such that we never operate transformer at this region. So in this region we never operate. In that 0.3, 0.4, 0.5 we never operate there, because it is near to maximum regulation. That's why if you know that this condition where we are getting maximum, we can avoid operation of transformer near to that point, so that our transformer will be safe. Drops will be less. And similarly 0 regulation. If you know that 0 regulation we will get at some 0.92 power factor leading, we never operate transformer near to that point. Near to that point we never operate, because 0 regulation also dangerous. Because 0 regulation means E2 equals to V2, no drops. But the problem is near to 0 we have negative regulation. Negative. There is a chance of immediate negative after 0, this side, left side. Negative regulation meaning is what? Terminal voltage is more than this EMF induced. Then as terminal voltage is more, current direction will reverse. Now secondary also will take the current. Already primary is taking the current from source. Now secondary also will take the current. Transformer action will fail here. Lenz's law will fail. That's why zero also should not take place, and maximum regulation also we don't want. To avoid the operation of transformer at the 2 points, we will find the condition for zero regulation and condition for maximum regulation, so that our transformers will operate in the safe region. Okay. So this regulation curve will give you answer for so many questions in the previous examinations. If you want, just observe the graph and try to look at the previous questions once. You can answer most of the questions very easily from this graph. But this graph, you should have clarity on this first. Okay. So this is our today's topic on the voltage regulation of transformer, one of the performance parameter. So we need low regulation, positive regulation. We need means actually very equal voltages, if they are, means zero regulation, that is best. But can we achieve that? Never. Because practically loads is lagging loads only. We don't have leading loads. Capacitive loads we don't have mostly. Overall power factor, if you calculate, we get lagging only, that is in the range of this 0.8, 0.9 UPF, in this range. So that always the regulation is some positive value, small value will be there. And maximum regulation of transformers will be around 4 to 5%, not more than this. But if you go to alternators, the regulation will be very high. So in that we have approximately in the range of 15 to 20% regulation we use practically. But transformer regulation is very less, 4 to 5% only maximum. But alternator we prefer high regulation. The advantage of high regulation in alternators is, with high regulation, the alternators are well protected from short circuit faults. So that you will know clearly in the regulation topic of alternators. Okay. So remember this topic so that you can answer most of the questions. So prepare well for any competitive examination further in future. So try to make every topic perfect so that you should answer very easy questions we get in the JE level, almost SSC JE or RRB JE, anything. Okay. So try to concentrate and try to listen the video lectures whatever you have from ACE Online. So it will help you very much, and practice the previous questions enough. Okay, all the best.
T20 and ESE 2021.
Hello everyone, my name is Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE Online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESC 2020 and ESC 2021.